Having studied some of the basic properties of the Riemann sphere in its three incarnations, namely C bar, the extended complex plane, P1C, the complex projective line, and S2, the unit sphere in R3, let us move on to introduce the next concept that is going to play a fundamental role in during the course, namely the concept of Möbius transformation. So maybe many of you have seen at some point the famous formula mu of z equal to alpha z plus beta divided by gamma z plus delta. And maybe you have been told that that is a Möbius transformation. Okay, but where does that formula come from, right? Why is it natural to consider that formula? Why that formula, not some other formula, right? So the natural context where Möbius transformations arise is actually linear algebra. We are going to see that this famous formula and the concept of Möbius transformation itself arises as the shadow of linear maps between from C squared to C squared at the level of the complex projective line. Remember that, recall from basic linear algebra that if we have a linear map, the image of any vector subspace is a vector subspace, i.e., if I have a linear map F from a vector space V to a vector space W, and if I take a vector subspace of V, the image of the vector subspace under F is a vector subspace of W. So in particular, if I take a bijective C linear map from C squared to C squared, the image of any one-dimensional C vector subspace of C squared is again a one-dimensional C vector subspace of C squared. And this means that our bijective C linear map F induces a well-defined function from P1C to itself. Namely, it maps any one-dimensional C vector subspace to the image of that subspace on the F. And that is what we call a Möbius transformation of P1C, or from P1C to itself. So a very straightforward definition that, as I said earlier, defines a Möbius transformation to be the shadow at the level of the complex projective line of a bijective linear map from C squared to itself. Some basic properties, which are I would say, practically obvious, are in this exercise 11, namely that every Möbius transformation is continuous. This is very easy to show. It's a very easy exercise on general topology, and the point is that it is induced by a continuous function from C squared to itself, which is constant on the fibers of the projection from C squared to P1C. So the continuity is fairly easy to show. It is also obvious that if I have the identity map of C squared, well, that it sends any subspace to itself. So the Möbius transformation associated to the identity is the identity of the complex projective line. That's also obvious. 3, it is very, very easy to see that composition of Möbius transformations, as defined here, is again a Möbius transformation, and that it is actually induced by the composition of the linear maps involved that gave rise to the Mobius transformations to begin with. And the reason it's fairly simple. So this is a fact which is very easy to see, because take first G for take the vector, take the linear map G from C squared to C squared, and then F from C squared to C squared, right? So we have the composition, and then so what's the image of a vector subspace under the composition? Well, it is the image of G of that under F. Right? So that is the image of that one-dimensional vector subspace under this one coincides with the image under F of the image under G. So we have this equality. So that's very, very easy to see. It practically comes down to the definition of composition of functions. Okay, and then next, every Mobius transformation is bijective. Well, this is clear from this and this, because from 2 and 3 we can deduce that that actually one can compute the inverse function as the Mobius transformation associated to the inverse of F. So of course, then this is bijective. And because we have already 1, 2, 3, and 4, we see that every Mobius transformation is a homeomorphism of P1 to itself. Indeed, every Mobius transformation is continuous. So if you give me a Mobius transformation of the form mu f, that one is continuous, but also its inverse is continuous. So it is a homeomorphism, right? Because mu f is continuous and its inverse is continuous as well. Okay, so this is very easy. Maybe I should just have stated it as a lemma instead of an exercise, because I pretty much already did the exercise for you. Okay, but then we can summarize this by saying that the assignment that to each bijective C-linear function from C squared to C squared associates the corresponding Mobius transformation. This assignment is a group homomorphism from the group of invertible C-linear maps from C squared to itself to the group of self-homeomorphisms of P1C. Okay. Now this is all very nice, right? But of course, at some point we want to really get a hands-on Mobius transformations, right? I mean, at some point we really want to perform explicit computations and see that these explicit computations allow us to establish some geometric facts about them. Right? So how do we do that? Well, we have defined Mobius transformations as shadows of C-linear maps, and we know that when we fix a basis of a vector space, then we can get our hands on to linear transformations by representing them via matrices using the given basis, right? And then and this is one of the things one does in the standard course of linear algebra. So we are going to just push what we already did in linear algebra, push it to P1C to obtain explicit formulas. So let's take an ordered basis of C squared. So we have seen already that that once we pick the basis B, we can parameterize P1C with a C bar in this way. That for each complex number, one considers this one-dimensional vector subspace with this representative, which is somehow special for the choice, for our given choice of basis, and representing representing the point at infinity of C bar as this one-dimensional vector subspace. We have seen that, and you see, so somehow this what this says is that if you give me this basis, we can get our hands onto the complex projective line, because we can get our hands onto these complex numbers and infinity, in the point at infinity. So take a bijective C-linear map from C squared to itself, and let's say that we compute its matrix with respect to the chosen basis, the basis that we picked. Okay, and then let us try to compute the value of the Möbius transformation at these two types of subspaces of C squared, explicitly in terms of of these parameters Z, and of course in terms of identifying this with a point at infinity. Okay, so for the first one, we by definition, a mu f of this vector subspace is the image of the vector subspace under F, which by the linearity of F can be computed as the vector subspace spanned by F of the special representative, which in turn can be written in this way, because here we know that the column vector of coordinates is Z1, and so the coordinates of the image with respect to B is given by simply multiplying this with this column vector. And this is how we know that f of this vector is equal to this. Okay, and then at this point we stop and we make a consideration similar to the one we did before, namely, I mean, we really want to write this in these terms. So we analyze. I mean, we analyze in the same way. The scalar that accompanies V2 is either 0 or it is not. If it is not, then we can divide by it. And when we divide by it, perhaps the vector changes, right? It's a scalar multiple of this one. Okay, but the vector subspace itself does not change. Okay, so this means that if this scalar is not 0, then we can write this vector subspace like this. And if it is 0, then this other one cannot be 0. Why? Because if both of them were 0, then we would have that f of this non-zero vector would be the 0 vector, but f was bijective. So if this one is 0, then this one cannot be 0, and then we can divide by it. And when we divide by it, again, the vector itself may change, but the vector subspace does not. And then we arrive at this, that in that case, this vector subspace is equal to this vector subspace, in this case. Okay, and then we play the same game with this other point, right? So notice that so far that this analysis applies to all of P1C except one point, right? So we are here. We already know the the behavior of mu f in P1 minus 1 point, right? P1 minus this point. Okay, but let's analyze what happens in this point. So in this point, we play the same game. Mu f of the space is the image of the space on the ref, which by linearity is the vector subspace spanned by applying f to the representative. Okay, we are using, multiplying this by 1, 0. We see that the image of this vector is alpha v1 plus gamma v2, and then we make the same consideration. If this scalar that accompanies v2 is not 0, we divide by it and we arrive at this. And if it is 0, then alpha cannot be 0, and then we can divide by it without changing the subspace, and we arrive here. Okay, so we have our explicit description of the behavior of mu f at any point of P1C. At any point of P1C, using the matrix that represents f with respect to the basis B. And something worth noticing is that that along the way, this famous quotient appeared, right? And actually, notice this applies to all of P1 minus 1 point. And the thing is, there is at most one set for which this is 0. At most one complex number for which this is 0. So so this means that that really mu f of a point is almost always equal to this, right? I mean, mu f of a point in P1C is almost always given by this formula. Almost always. When can this formula not be applied? Well, first of all, in this point, we are not applying really that formula, and second here, right? But you see, I mean, somehow this quotient really governs the behavior of mu f almost everywhere. That's my point. Okay, now let us pool these computations to C bar. So far we have defined the concept of Mobius transformation for P1, for P1C. Now we know that P1C and C bar are homeomorphic. So it makes sense to see how these functions, how they can be expressed for C bar, right? I mean, in other words, we want to derive an explicit formula, but for C bar. Okay, so now the homeomorphism is defined for each basis, right? So again, I suppose that my basis B is fixed a priori, and then if I have a Mobius transformation of P1, what I have is this mu f, but then I also have phi B inverse, which goes to C bar, and I want to investigate, this map from C bar to C bar to see what formula, by which formula it is given. So this formula itself tells me, whenever you have a vector subspace expressed in this form, so as spanned by something that has a 1 accompanying V2, then just keep Z, right? So that's the behavior of phi inverse. And for this other vector subspace, which is really just the multiples of B1, what you keep is infinity. So when we apply this to these computations, we see that that if gamma set that when we have a complex number set and if gamma z plus delta is not 0, then we get to keep this point, right? So we have this rule. But if it is 0, then we keep we say, okay, we keep the point at infinity. So we have this rule. And here, otherwise, you know, for the point at infinity, if gamma is not 0, then I keep this scalar, alpha divided by gamma. But if it is 0, what I keep is the point at infinity. So we have this formula, which is the famous formula that we've mentioned a couple of times. Which here, by the way, I'm sort of repeating myself, but notice that this is the formula that dominates, because almost, you know, given z in z bar, only one point in c bar is not a complex number, namely point at infinity. Only one of them, and there is at most one point where gamma z plus delta is equal to 0. So for any given, you know, for at most 2 points, it is that I cannot apply this formula. So that's the formula that really dominates. And this can be seen kind of as special cases, right? But the thing is, for, you know, if this happens, as we have seen, then alpha z plus beta cannot be 0, right? Because the linear map was bijective, because mu f was bijective, because f was bijective. So somehow the thing is, we can make the convention of that if I have a non-zero complex number divided by 0, then say, okay, then in that case, then just define that to be equal to infinity. So take this convention. Likewise, you know, for set equal infinity, and if, you know, for set equal infinity, what one can say is, okay, so take this expression, and then to investigate what the value at infinity should be, you just take the limit when the complex number z goes to infinity, and the limit, then you can say, okay, so that's the limit of, you know, of plugging in infinity. Sorry, that's the value. That limit is the value of plugging in infinity. So we can make that convention, and if we take that convention, then in this case we have alpha divided by gamma, and in this case we would have just infinity, because then here we would have 0, and then this limit would be just when z goes to infinity would be infinity. So if we impose these conventions, we see that then actually this is given just by this formula. Right? So we already knew that the formula applied for everywhere except in at most 2 points. But we can make sense of saying this equal to this everywhere with these conventions. So we are going to adopt these conventions even without any further apology. So I may not even mention these conventions again. I'm going to just adopt them. Okay. Now notice that saying that to z we assigned this only needs to know to have a matrix. So that's what we do. So while we define the Möbius transformations of P1 in terms of linear maps, so as associated to bijective linear maps, what we're going to do is to define the notion of Möbius transformation of C bar as associated to invertible matrices directly, without passing through necessarily through linear maps. So for each invertible matrix A equal to alpha, beta, gamma, delta, with complex entries. We define a function from C bar to C bar by the rule, just by this rule with these conventions. Okay, and such functions, the functions of the form mu A for A invertible with complex coefficients are going to be called, so those functions are going to be called Mobius transformations of C bar. Okay, so Mobius transformations of P1 are associated to linear maps. Mobius transformations of C bar are associated to matrices. And now, and then just let us write the relation between the two notions very rigidly, just to avoid confusions. So if we fix any basis, if we are given a basis, and if we are given a C-linear transformation, then the way we express the Mobius transformation of P1 associated to F is given as this composition, where of course we first go to C bar, and then in C bar we apply this formula here, this definition here, and then we go back to the complex projective line. Right? So I'm pretty much just rewriting this. Right? So that's the relation between mu f and mu of its matrix. Right? Okay. Now let us give some examples. So all of this is very nice, but it would be nice to give some concrete examples, and if possible to have some basic geometric analysis of these basic examples. Okay, so let us give some examples of Mobius transformations. So we start by giving some basic examples, some obvious examples of Mobius transformations. The idea is that there are certain obvious functions for which an analysis of the geometric behavior can be done, because the functions are defined in very simple terms, are very accessible. And it turns out that many of these obvious functions are Mobius transformations. So we start our study of our systematic study of Mobius transformations starts by first studying the obvious ones for which the geometric analysis can be performed in a very simple-minded manner, and then later use some kind of force the machine so that one can describe the geometric behavior of any transformation by means of the geometric behavior of the obvious Mobius transformations. So one of the most obvious ones are translations. So take a complex vector, a complex number beta, and think of it as a vector along which you want to translate. So it sends z and a complex number z to z plus beta. So that's the correspondence rule of this function. And then of course the first thing is, okay, so is this really a Mobius transformation? Because if it is going to be a Mobius transformation, we have to be able to present this assignment as arising from a square matrix, right? As arising from a square matrix via this formula that we saw. But that's quite easy. So if you play with this this matrix 1 beta 0 1 realizes the translation by beta as a Mobius transformation. Notice that infinity is a fixed point. So I mean, just play with the formula here, or sort of notice that complex numbers, they are all moved, and then infinity, well, somehow infinity, you have to keep it where it is. So infinity is a fixed point. And well, it is very easy to see that the identity is achieved as the translation by nothing, right? And that's the only way to get the identity as a translation. Okay, so very obvious functions, translations of the complex plane, now extended so that to get maps from C bar to C bar by setting infinity to be a fixed point, and now some basic analysis of the geometry of this Möbius transformation. Well, for instance, what do I mean by some basic geometric analysis? Well, for instance, to find certain curves that are invariant, or I prefer to say stable on the translation, and even better by all the integral powers of the Möbius translation of the Möbius transformation of the Möbius transformation of this translation. Well, it is clear that the parallel lines to the vector beta, to the lines that are parallel to the vector beta, each of them is stable by iterated translations in both directions, right? I mean, so by all integer powers of this transformation. Okay, and that's what I mean, that the translation is such a simple function that one can just see it, that these curves are one can just find them immediately, a family of curves that are stable under this action. Notice that these curves, I mean, I don't really need to think about, okay, curves that are stable under the integral powers of this and contain infinity. Well, I don't need to worry about putting infinity in these curves because infinity is a fixed point. So what I really care about is about C, somehow about being able to cover C. I mean, to express C as the joint union of these curves. So in other words, C bar minus the fixed point. Okay. Now, what other question can one ask? Kind of geometric question to have certain mental idea, mental image of the geometric behavior. Well, about curves that are that kind of a family of curves that go to each other on their iterated translations. That I mean, a family of curves that preferably also allow it's a family such that C bar minus the fixed point is the disjoint union of these curves, and that they are permuted by mu1 beta 0 1. Okay, so think about it, and well, okay. I mean, this family, the family of lines, of straight lines parallel to beta, has this property, but it is kind of boring because each one we know it's already stable. So the way the Möbius transformation permutes the family is trivial. It just permutes it as the identity, right? But something more interesting, well, any other family of parallel lines, so a family of parallel lines not parallel to beta, is permuted by translation by beta. Sort of somehow, so we have many different families of curves that cover C disjointly and is permuted by the action, right? Because it doesn't matter if the if this family of lines is, for instance, orthogonal to the family of lines parallel to beta, or what if it forms another angle different from 90 degrees. Okay. Okay, and this is some basic basic analysis. And there are some other families of curves. And for instance, think about, in a concrete example, think about translation, vertical translation by the complex vector I, by the complex number I, so the vector 0, 1. Well, of course, let's say the family of all horizontal lines is permuted by this translation. But also, for instance, let's say take the graph of the cosine, for instance, so the graph of cosine, and take all the translations of that. So take all the curves of the form complex number plus cosine. This one also has the property of being permuted. This family, when we allow the complex number that we add into cosine to vary, is permuted by the vertical translation by the complex number I. So it is possible that there may be many different families. To find different families, each of which is permuted, in each of which the Möbius transformation acts by permutation. Okay, so next example. Another obvious type of function is, well, I mean, someone can say polynomial functions, right? So that they are maybe the next obvious ones. Yeah, okay, but for instance, z goes to z squared. Can it be a Möbius transformation? Well, no, because it is not injective, right? It is not, z goes to z squared is not a Möbius transformation of C bar. Okay, but then what else? Then you can say, okay, actually this same argument kind of excludes like all polynomial functions where the polynomial has degree greater than 1 because of the injectivity. Because well, okay, one has maybe to be a bit careful. But anyway, okay, and then you can say, okay, then that more or less leaves you with linear polynomials. Okay, so polynomials of the form alpha z plus beta. Okay, we already saw translation is Möbius transformation. So the next obvious one is actually just multiply by a complex number. Okay, now multiplying by 0, of course, is way far from being bijective. So take a non-zero complex number and consider the function multiplication by alpha. Okay, multiplication by alpha, which if you think it doesn't give you much choice about the behavior at infinity, you have to fix infinity. And it fixes 0 as well. Okay, and how is it a Möbius transformation? Well, to see whether it's a Möbius transformation, we have to realize it as the Möbius transformation of associated to a square matrix. Okay, well, but that's rather easy. Right? Okay, so multiplication by any non-zero alpha is a Möbius transformation. We notice this. It has two fixed points. This Möbius transformation, namely 0 and infinity. Also, you can obtain the identity this way, well, when alpha is equal to 1, right? And also, we notice that well, this identity, which I would say is it is obvious, right? I mean, this is repeated multiplication by alpha n times, which is equal to multiplying by alpha to the n. and this matrix is obviously equal to this matrix. So so we have this, which can also be seen as something that we already proved, namely that that associating to each matrix its Mobius transformation is a group homomorphism. And then you may say, no, wait, you didn't really prove that, because we proved that we have a homomorphism from the group of invertible C-linear transformations of C squared to the group of homeomorphisms of P1. It's not quite GL2C, and it's not quite the homeomorphisms of C bar. Okay, fair enough. But we already know that this was a homomorphism. The proof was very easy. The proof really boiled down to the fact, to the definition of composition of functions. And you see, once we, and because of this relation, it turns out that associating to each matrix its Mobius transformation is a group homomorphism from GL to C, that is the group of invertible 2 by 2 matrices with entries in C, to the group of cell homeomorphisms of C bar. And then knowing that this can be seen as a consequence of that. Although the first argument I gave is just a direct argument for this one. Okay. And now the next thing, kind of the promise, right? That these functions are so simple-minded that one can develop a basic analysis of its geometry, of their geometry, this type of functions. Okay, and here it turns out that one has to be a bit careful on where alpha is located, about alpha. And so what it turns out, I mean, and it's actually just a moment of thought about this alpha. So it's not very hard to see that the geometric behavior depends on whether alpha is 1, of course, right? When you have the identity, when alpha is a positive real number, excluding this number 1 that induced the identity, or it is in the unit circle, excluding excluding 1, and the rest. So the geometric behavior of this mu alpha 001 depends on which one of these sets alpha is taken. And these sets, of course, I mean, they give me a partition of C minus 0. Right? And the partition you can visualize it here, right? I mean, here is 1, here are the positive real numbers different from 1, the circle minus 1, and the rest. The rest including negative numbers, right? Of course, including all of them except minus 1. Okay. So let us go step by step. So of course here, this one gives me the identity. And we already saw that the only way to get the identity is when alpha is equal to 1. Okay, so the next possible choice of alpha, when it's a positive real number different from 1. In that case, what I obtain is a homothety, right? I mean, each non-zero complex number gets either longer or shorter when I multiply by alpha, depending, of course, on whether alpha is greater than 1 or not, right? If it's greater than 1, then the image of any vector is larger than the vector. If alpha is less than 1, vectors get shortened when multiplying by alpha. Okay. Right. Uh, and then one says, okay, this what I just said. I mean, it's clear that when one asks about a family of curves that covers C bar minus the fixed points. I mean that all of them disjoint, right? But that are each one of them stable on their multiplication by alpha. Well, the positive rays, right? I mean the positive real multiples of any given non-zero complex number. Mm-hmm. Each one of these curves is stable on their all integer powers of multiplying by alpha. So this is clear. This is very basic analytic geometry. Mm-hmm. So we see that one immediately succeeds at finding a family of curves that gives me a partition of C bar minus the fixed points, and having each of its members stable under the action of this one. Right? It's the integer power. So under the subgroup of Homeo C bar generated by this guy. Okay. Here it's something. I mean, I already mentioned that when alpha is greater than 1, then multiplying by alpha enlarges each vector. It makes each vector longer. And actually, what happens is that if I keep iterating multiplication by alpha ad infinitum, I always get to infinity. Right? I mean, for any z different from 0. This means, so no matter which z I take, as long as it's not 0 or infinity, this limit is always infinity. Right? So somehow, if alpha is greater than 1, the fact that multiplication by alpha enlarges the vector ultimately implies that somehow 0 is some sort of repulsor of the action, and infinity being always this limit for z different from 0 is an attractor of the action. Right? So somehow the two fixed points do not have the kind of the same nature. One of them is a repulsor, and the other one is an attractor. Right? So this is kind of funny. So we have two fixed points, but the two fixed points do not quite have the same nature. Similarly, if alpha is different from 1, or conversely, if alpha is less than 1, then we have the other situation. So namely, iterating the Möbius transformation at any given set different from infinity tends to 0. So when alpha is less than 1, now everything different from infinity is attracted to 0, and gets away from infinity. Okay. Which is kind of consistent with the fact that, for instance, if you take alpha greater than 1, then the inverse of the Möbius transformation is the Möbius transformation of the same type that corresponds to alpha inverse, and alpha inverse in that case then is less than 1. So if in this case everything got away from 0 and went to infinity, well, for the inverse, which is given by a number less than 1, get things back in place, right? So it attracts things to 0. Okay. So, and here we can see the kind of I would say nice picture where one sees this family of curves, of stable curves, which are these open rays open rays going from 0 to infinity. Okay, and then of course there is the question of well, now that you have found a family of curves stable under the action of the subgroup generated by the Möbius transformation, can you give now a family of curves that give you a partition of C bar minus the fixed points, and where the Möbius transformation acts by permuting the curves? And then just think about it. Well, any circle, if you have a circle, when you multiply it by alpha, you get another circle. So the family of circles centered at the origin, for which we can obviously say they give you a partition of C bar minus the fixed points, which are 0 and infinity. So very easy to find them. And here, notice that there's something funny about these two families, namely the family of these arrays, of the arrays of the open rays connecting 0 with infinity, and the family of circles centered at 0. And is that the two families are orthogonal. And by saying that the two families are orthogonal, I am in particular saying that every member of one family is orthogonal to any member of the other family. So no matter which one you take here, and no matter which one you take in the other family, they are orthogonal. Just something to notice. Right? Okay. Something that we could also find in the case of translations. Okay, so let's move on to the next possibility for alpha, which is when we take it in the circle, and of course different from 1. Well, in that case, multiplying by alpha is a rotation, right? Actually, if we write alpha in polar form, then multiplication by alpha is rotation by the argument of alpha. Okay, this makes it immediately clear that every circle centered at the origin is stable under the action of the subgroup generated by the Möbius transformation. Subgroup of where? Subgroup of which group? Of the group of self-homeomorphisms of C bar. Okay, so again, we immediately find a family of curves, each of which each curve being stable under all integral powers of my function. Okay, how about the other family? Or to be a bit more accurate, maybe a bit more pedantic, how about some family of curves that partition C bar minus the fixed points, which are 0 and infinity, and where the Möbius transformation acts by permuting the curves in the family. Again, if you take any open ray and you rotate it, you get another open ray. So actually, it's kind of the rays, the open rays through connecting 0 to infinity, they form such family, right? Rotation, multiplication by alpha, which is rotation by theta, permutes them. Permutes the family of curves, right? In the sense that each member of the family goes to another member of the family. The image of any member of the family is a member of the family, right? And here what I said orally, was about the open rays, and what I wrote was the straight lines I think I actually prefer the race, the open race, because somehow I'm interested, you know, in foliating C bar minus the fixed points, okay? And you know, this one of course has one of the fixed points. Anyway, what else? One last piece of analysis for this in this situation. Well, that while in the case of translations, as long as of course as long as it's not is not the trivial translation, not the identity, this one has infinite order, right? There's no coming back, right? I mean, if I start applying the translate by beta and then by 2 beta and then by 3 beta, there's no coming back. So this one has infinite order always, provided it's not a trivial translation. Something similar for in the case of having a positive real number different from 1. There's also no coming back. So they also have infinite order always, regardless of whether alpha is greater than 1 or less than 1, always. But here some of them have finite order and some of them not. And the characterization is that you have finite order precisely when the angle rotation is rational. This is something it's not hard to prove, so I just leave it as an exercise for you. Here in this nice picture, you can see the family of a sketch of the family of curves that are stable under the action of the subgroup generated by the Mobius transformation. Okay, and then the final case, which is when you know in the remaining situations. So for the complex numbers that we haven't considered so far. What we are going to obtain are what we're going to call them Loxodromies, and they are actually kind of commutative composition of a rotation and a homothetty. So, I mean, just think about it. Write alpha in polar form, and of course, first multiplying by just this element of S1. I mean, this complex number of norm 1, and then by the norm of alpha. Of course, it commutes. If you first multiply by this and then by this, you get the same thing. So in this case, you can always write the Mobius transformation as either rotation followed by homothetty or homothetty followed by rotation. Okay, fairly easy. Now, we are asking. We have been asking in each case about a family of curves that partition C bar minus the fixed points, and having each curve belonging to the family, stable under the action of the Mobius transformation. So we want, you know, we want curves that are invariant, that are stable under multiply by alpha and multiply by alpha, multiply by alpha, multiply by alpha. And then well, what I'm going to do, just to do everything at once, is not only find kind of an obvious curve, which with this property, which is just the curve parameterized by the real line, that such that gamma of t is alpha to the t. Right? So not only that, but I'm going to rotate them because you see, if you rotate and then you start multiplying by alpha, you still have something stable under multiplication by alpha. So for each element of the circle, and here without excluding one, right? Because yeah, I mean, it's a different consideration. So for each element of the circle, so for each complex number of norm 1, consider this curve, the curve which is alpha to the t, but rotated by this element of the circle. By the way, alpha to the t, we define it as this. So I take that as a definition. I take this as a definition of alpha to the t. Because I mean, alpha to any integer, it always makes sense, right? But alpha, and we can make sense of alpha to any rational number. But how about alpha to an irrational number? Something has to be done, and that's what we do. Okay. I mean, I'm sure you saw this in your courses of complex and basic complex analysis. Okay, and now the point is that by the famous theorem of de Moivre, we actually have, you know, multiplying gamma s of t by alpha, actually, excuse me, multiplying by alpha actually gives you, you know, gamma s in t plus 1. Right, because multiplied by alpha, and then the Moivre's theorem tells you that then, you know, alpha times s alpha t is equal to s alpha to the t plus 1. Which, by the way, I mean, somehow this has to be shown. This has to be proved somehow, because for t integer or for t rational, this may be kind of sort of clear, but how about irrational, right? So anyway, so we just recur to the Moivre's theorem, and this tells you formally that that the image of gamma is stable on the multiplication by alpha, because when we multiply by alpha, we can express it as another point on the curve. Okay, so indeed these gamma s's, these gamma s's are stable under multiplying by alpha, and actually under the whole subgroup of Homeo C bar generated by the Mobius transformation. Okay. How about another family? Now how about a family that partitions C bar minus fixed points, which are 0 and infinity, and where the Mobius transformation acts by permuting the members of the family, the curves in the family. Well, again, this one is not so hard. So while maybe this one, you know, this I give it to you that maybe this one is not as obvious as in the previous cases. I admit that this may be not so obvious, but for the family of curves permuted by the Mobius transformation, it really is that really is obvious, because multiply by alpha, and you know, multiplying by alpha is rotation followed by homothety. So rotation followed by homothety. So the circle centered at infinity, the family of circles centered at infinity, sorry, not at infinity, at 0. Well, they are also centered at infinity. So what I said is not wrong. But the family of circles centered at 0 is permuted by the Mobius transformation, and this was very easy, right? So this may be not so easy, but the other family is very easy. And let's just close this analysis by saying, okay, so how do these curves look like? Okay, so let's just recall that the parametrization, the usual parametrization of the circle, which is the function from R to the complex numbers that associates to each t cosine of t plus I times sine of t, what it does is it traverses the unit circle in the counterclockwise sense, right? I mean, so if alpha is greater than 1, this curve, which is, you see, cosine plus I times sine times something. If the norm of alpha is greater than 1, then it starts getting far away from the origin as the parameter t increases. So if the norm of alpha is greater than 1, we start, you see, when as t increases, you start, revolving in the sense, in the counterclockwise sense, and getting away from 0. Okay, and similarly, when the norm of alpha is less than 1, when t increases, you start getting smaller and smaller and smaller, close to 0. So again, when alpha is greater than 1, 0 is a repulsor and infinity is an attractor, and when alpha is less than 1, infinity is a repulsor and 0 is an attractor. Yeah. Right, because it's when t increases, but you see, multiplying by alpha adds 1. So if you keep multiplying by alpha, the limit is you are letting the t increase. Okay, so now some terminology. These curves or its images are going to be called the Loxodromies associated to alpha. And then of course that immediately brings the point of then maybe I should use some notation that makes reference to alpha. Okay, I'm not doing that at least for the moment, but if necessary, I will do something like gamma alpha comma s, or gamma s comma alpha, or gamma s alpha, or something. But for the moment, no. But it is important that this family of curves, that the family of curves depends on alpha, right? Each curve in its definition depends essentially on alpha. So yeah, and actually you see, having a large norm means somehow that this opens very quickly. Having, let's say, something very close to 1, greater than 1 but very close to 1, means that okay, this opens, but maybe not so fast. Okay? So maybe one gets something like this, or maybe one gets something like this. Okay, I mean, I'm just trying to illustrate that indeed things depend on alpha. Right, and now see, we saw. I mean, so far, we have seen that in all these cases, for translations, for multiplication by a positive real number different from 1, and multiplication by an element of the circle different from 1. The family of curves stable under the action of the Möbius transformation that we found, and a family of any of the families that is permuted by the action that we mentioned, right? I mean, in the case of translations, there are many. In the case of homotheties, we only gave one family. Also in the case of rotations, But in all of those cases, it doesn't matter which curve in one family I take and which curve in the other family I take. So which curve in the family of stable curves and which curve in the family of permuted curves. It doesn't matter which one I take here and which one I take here. The angle they form in their intersection is always the same. And so of course here we have the question whether any of these loxodromes and any circle centered at 0, also centered at infinity, so it's correct, whether they always form the same angle. And the answer is yes. So the angle of intersection of the loxodromes associated to alpha, so for fixed alpha, with the circle centered at the origin, that angle is always constant. It's always the same. And I find the proof, I would say, quite beautiful. Okay, so let us prove the theorem. So first, very briefly, let me describe the overall strategy of the proof. So take any loxodrome associated to alpha. So of course there's one loxodrome associated to alpha for each value of the circle, right? As we have said. So okay. So we take one of them, gamma s, and then the first thing we noticed was that if the curve is closed under multiplication by alpha, right? In other words, if I take any point, then multiplying by alpha is again in the curve, right? If I take any point in the curve and I multiply it by alpha, the result is again in the curve, right? But actually, notice that if I take any point in the curve and I multiply it by alpha t for any real number t, the result is again in the curve, right? So the curve is not only closed by multiplying with alpha or with integral powers of alpha, it is closed by multiplying with any real power of alpha. And moreover, if I fix a point, if I take a point in the loxodrome, then every other point in the loxodrome can be obtained by multiplying this given one by some appropriate power, real power of alpha. In other words, everything can be written in terms of any given point of the loxodrome by multiplication by real powers of alpha. Okay. Okay, so what I'm going to do is I'm going to look at the unit circle, look at this point of intersection, and then see that when I multiply, I look at this point of intersection, and then I have this angle, right, between the unit circle and the loxodrome. And what I'm going to see is that after multiplication by alpha t for any real number t, the point where I land, in the image of this intersection point, the angle is again the same as the angle formed here, and that suffices to show everything, because this means that for any given circle where I take the point of intersection, this point of intersection is of the form alpha t times this point for some t, and then this angle is equal to this angle, equal to this angle, equal to so on, so on, so on, so on, so on, so on. And then how do I show this? So at least between this loxodrome and any other and any circle centered at 0, the angle would be constant. And then how do I move on to the other loxodromes? Well, the other loxodromes is kind of just you obtain just by rotating the picture. So you rotate the picture so the angle doesn't change, and then the theorem follows, right? So it suffices to show that that after I multiply with alpha t for an arbitrary value, real value of t, the angle here is the same as the angle here. So this is the overall strategy. So let's do it. Let's go on to the formal argument. So for each real number t, we consider the function multiplication by alpha to the t, as we said. Alpha is not 0, so alpha to the t is never 0. So alpha is not 0, so alpha to the t is not 0. And now this function, as a function from C to C, is holomorphic with a complex derivative, actually alpha to the t everywhere, right? This is the derivative everywhere, and it's non-zero. So this map is conformal. That's the key point. It's conformal, so it preserves angles of intersection. So when I consider the unit circle and my given Loxodrome, the angle at their intersection point, which is easy to compute, right? Because this one is on this point S is on the circle and on the unit circle and on the Loxodrome. So when I measure the angle at the point of intersection, this angle is equal to the angle formed by by ft of S. I mean by the result of evaluating my conformal map in S. Formed there by the images of the unit circle and the Loxodrome. Now, well, the image of the unit circle is a circle. It's a circle also centered at 0. That's the thing. And this one is actually the Loxodrome itself, because we have this computation, right? So this computation implies that that actually this one is the Loxodrome. This image is the Loxodrome. So the image between the unit circle and the original Loxodrome at their point of intersection is equal to the image at this point, which is the point of intersection between the image of the circle and the image of the Loxodrome, which is this one. So when in this point of intersection, the angle is the same as the original angle, and we are done. So I think it's a very nice proof. Okay, and then just finally a remark that I've been saying all throughout the class, which is that in all the standard examples we have analyzed so far, in each of them we have been able to express C bar minus the fixed points of the Möbius transformation as disjoint union of two different families. So first, given our Möbius transformation mu a, we have been able to express C bar minus the fixed points as the disjoint union of a family of curves, each of which is stable under the action of all the integral powers of mu a on the one hand. On the other hand, we have also been able to express C bar minus the fixed points as the disjoint union of a family of curves, which is permuted by mu a, by which I mean that for this given family, the image of any curve under the Möbius transform of any curve in the family under mu a is again in the family. Okay, so we have been able to form some sort of grid that covers C bar minus the fixed points, and it has somehow like complementary behavior. On the one hand, for a family, for one of the for a family, they are all stable, and for the other family, they are all permuted. This will be very helpful later on. And one last remark is that in all the standard examples we have analyzed so far, it is obvious that the given Möbius transformation sends circles in C to circles in C. Right? So this is clear for translations, homotheties, the rotations, and also the Loxodromies we have seen. So even if the circles are not centered at the origin, right? So it's circles in C bar. Circles in C bar. So the image of any circle in C is a circle in C bar. It doesn't matter that the circle, the original circle, is centered at the origin or not. And also the image of a set of the form straight line union infinity is also a circle in C bar. And this is obvious in the examples we have seen so far, and will be very, very useful later on. So summary of today's class. So first of all, we introduced the notion of Mobius transformation as a linear algebraic concept. So we defined the notion of Mobius, and we defined a Mobius transformation to be the shadow at the level of P1C of the bijective linear maps from C squared to itself. Then we made some explicit computations with respect to any given basis of C squared. And then we saw that having any given basis of C squared, we can perform some explicit computations and arrive at some explicit formulas for the correspondence rule of any Mobius transformation of P1C. Okay, then later on, recalling that we had already established a homeomorphism between C bar and P1C, we pulled the computations we did for P1C to C bar, and then this motivated us to define the concept of Mobius transformation of C bar as a function given by the famous formula associated to an invertible square matrix with complex coefficients. Then we went on to give some standard examples to see that some obvious functions from complex analysis are Mobius transformations, and then these standard examples were first of all the translations, second multiplication by a non-zero scalar alpha, which was subdivided into cases depending on whether alpha is a positive real number, an element of the unit circle, or a complex number not in one of these sets. And then we saw that, so we made a basic analysis in each of the standard examples, and we were always, in these examples, we were always able to find a family of curves stable under the action of the integral powers of the Mobius transformation, and also another family of curves. We were also able to express C bar minus the fixed points as the disjoint union of a family of curves permuted by the Mobius transformation. Okay, and finally, we showed that just as in the case of translations, homotheties, and rotations, where these two families, the stable ones and the ones permuted, at least in the families the explicit families we saw, that the angles formed between one family and the other were constant. We established the same result for the Loxodromies. So that the angle formed by the stable curves and the curves permuted is always the same. And that was it for today's class.